Good afternoon. Thank you. It's a pleasure to be able to introduce this afternoon's topic of focus, which is the modelling of climate risk and natural catastrophes in the context of a changing climate. And we have three expert speakers joining us this afternoon to take us through to the break. And then after the break, we'll be hosting a modelling roundtable with the providers of the major and leading catastrophe models that are used by the insurance industry. And so I'd like to invite the three speakers for this afternoon's sessions to join me up here on the stage. And that is Anthony Davison, Philippe Nouveau, and Nicolas Trey. And then I'll start the session with a few introductory comments before leaving them to give their presentations. And we hope to have, similar to earlier this morning, we'll have some time for Q&A at the end of when the speakers have delivered their presentations. So the modelling of climate risk it's a topic very close to my own heart. I've spent the last 15 years of my career dedicated to this topic, focused on the modelling of natural catastrophes for the insurance industry. And during that time, I have been deeply involved in the multiple catastrophe events that have happened over the past 15 years. And I've come to realise that the one common factor that unites all of these major extreme events is that they're all unique. By their very nature, extreme events are rare. Thus, we do need the models to help us understand the extreme events that are beyond our experience. The scientific field of modelling has advanced significantly, certainly in the last 15, 20 years, through the integration of the research that's happening around the world, the systematic study and investigation and learning from events when they do happen, and of course the technology, as we heard about earlier today, that enables things like the climate models, which are increasing in both their resolution and their accuracy with time, even given the limitations that remain as were described earlier today. We, of course, need to remember that models are models, and they're not to be held up as exact representations of reality. And understanding the uncertainty in the models and understanding what we don't know can be as important as understanding what we do know in the models. And I think some of the debate we were having earlier around where is there still, how good are the models at different time horizons is a very important one for all of us to understand and be very cognizant of as we try and use these models for making better decisions. It's certainly a learning path that the insurance industry has been through. Just 20 years ago, really, 25 years ago, the insurance industry had really very little idea of the potential consequences that it could be exposed to before the likes of Hurricane Andrew in 1992, and they're very shortly followed after that by the Northridge earthquake in 1994. But since then, the development of the catastrophe models have helped the insurance industry become increasingly resilient. And that has come together with the skills of planning and critical thinking within a probabilistic framework. And I think this is a framework that can be applied more broadly outside of the insurance industry. So there's a great opportunity facing us to be able to take these techniques and these models and this ability for critical thinking and apply them more broadly to planning and policy making, which is what these 2 days are very much about. But there do remain the uncertainties, as I mentioned earlier. So there remain uncertainties in our understanding of the events and their consequences, and thus there remain uncertainties in the models that we're using to understand those events. And the newest uncertainties are continuing to arise. So, for example, what is the impact of increasing CO2 emissions on both event severity and event frequency? And it's against that backdrop of increasing population and industrial output, which continues to outstrip the increase in population. So industrial output increasing growth rate at around about 3 to 4% per year compared to an annual human population growth rate of about 1% a year, which signifies that the world is there is more wealth, there is more goods, and there's more trading and shipment of those goods. And that industry and those people like to be in quite high-risk areas. Again, this was touched upon earlier, and the debate rages as to what is the balance between its increasing populations and wealth exposures in exposed places, such as coastlines, versus increasing in the frequency or the severity of hurricanes, for example. And this is something that models can help us start to understand. And we're seeing that the science of statistics is being applied to understand attribution. Detection and attribution, and we'll hear a little bit about that this afternoon. So we can detect that there are changes happening, and when increasingly statistics is helping us understand to what degree are these events the probability is being influenced by CO2 emissions versus natural causes, for example. Now, the reality is that climate change also operates on multiple timescales, and it has multiple influences. There are annual timescales and influences, there are multi-decadal influences and timescales, and there are longer-term, decadal and centuries-long influences. And each of those timescales has a mixture of natural causes and the human-driven CO2 injections that are happening as well, as we heard about earlier. Our collective work as scientists and as modelers is to capture that full landscape and build it into models and tools that are useful. And I refer there to the great quote by I'm sure many of you will know, the quote by the great statistician George Box, who said that, famously, he said that all models are wrong, but some of them are useful. So that is our challenge as modelers, is to make models that are useful, for the end purpose, whether that's planning, whether that's very long-term planning and policy making, or shorter-term investment decisions. And we need to use the right models for the right timescales that we're concerned about, depending on the problem that we're trying to solve. It's also an opportunity for us to not just bring the models and techniques that have been used in the insurance industry to a wider audience, but also for the industry to connect with a broader community as well. A broader community of academics, of policymakers, and of planners. I'm very pleased to be able to announce today that SCOR it's in the process of joining Climate Kick, which is an EU-wide initiative for climate change innovation. It's bringing together multiple stakeholders across Europe to tackle the new challenges that are being posed by a changing climate on top of the landscape of global development. With doing so, we will become the first insurer to join this organization, but I very much hope that we won't be the last by any means. As I think it's really important that this collaboration continues to increase and we work in multiple dimensions and with each other to solve the bigger problems. But undoubtedly, the starting point to managing risk is to understand it. So this afternoon, we're going to hear from the experts in the modeling to help us model and therefore understand and manage the risk. So I will now just introduce briefly the three speakers before inviting Anthony up to present. So first of all, Anthony Davidson. He is Professor of Statistics at the École Polytechnique Fédérale de Lausanne. His current main research interests are the statistics of extremes and the development of suitable methods for modeling these very rare spatio-temporal events, particularly, but not limited to, within the context of climate change. He's an editor of the leading research journal Biometrica, and in 2015 received the Guy Medal in Silver of the Royal Statistical Society. He'll be talking to us today on the topic of risk and the statistics of extremes. Philippe Naveau is a research scientist at the French National Centre for Scientific Research. as well as being a visiting scientist at the National Center for Atmospheric Research in Boulder, Colorado. His research focuses on environmental statistics, and especially in analyzing extreme events. Part of the work of his group is focusing on the statistics of detection and attribution, as I discussed earlier. And then finally, we have a presentation from Nicolas Trey, who is the research director at INRA, the French National Institute for Agricultural Research. He's also director of Toulouse School of Economics, thematic group Environmental Economics, and he is the co-editor-in-chief in the Geneva Review of Risk and Insurance. His research concerns risk and decision theory, as well as environmental economics and benefit-cost analysis. And he'll be talking today on the topic of catastrophe aversion. So with that, I'd like to ask Anthony, the first speaker, to come up. Thank you very much.
After these splendid talks this morning, and large scale, and this lovely introduction, I feel rather like the English novelist Jane Austen as I stand here before you. Not that she was known to have sported a beard, or that she studied mathematics so far as we know, but more that what I'm going to talk about is going to be a very, very small part of her. She famously said of her novels that they were like a very small piece of ivory worked over with a very great care, and I feel as though I'm going to talk about a very, very small part of risk modelling. The topic is risk and the statistics of extremes, and I'm not quite sure how this thing works. I guess it's this, is it? Ah, yes, perfect. The work's partly funded by the Swiss National Science Foundation, and it's been done with a huge variety of collaborators. The most important of those you see on the screen here, Payman Assadi, Sebastian Engelke, Simone Padoan, and Mathieu Ribate, not coincidentally from 4 different countries. What we want to be able to do is to forecast future risks, future rare events, and of course for all sorts of reasons. There's the question of disaster planning for flooding, windstorms, food security and so on. Public health, on which we had a very interesting talk this morning. Construction, which hasn't been mentioned yet today. But of course the future environment's not going to be like the past environment, and we'll need to be able to build things in different ways to be sure that they're going to be habitable and will be sustainable in 100 years' time. And of course insurance. The fundamental problem we have to deal with as scientists is extrapolation. And what we want to be able to do is to extrapolate it to large, rare, complex events that could occur now, but perhaps only with very low probabilities, and also into a future that's not going to be like the past or the present. So we've got 2 sorts of extrapolation that we need to do. One, somehow beyond the tails of things we can see now, and another because the changes that those tails will change. The environment, as we've seen this morning, very convincingly, is increasingly non-stationary. So past data are going to be relevant, but only indirectly so. We can't just do rechurn historical data and hope to be able to make realistic forecasts. And what that means is we're going to need models. We're going to need models that we can justifiably, but as Claire just said, carefully and humbly, because of the uncertainties involved, try and extrapolate to see probabilities, estimate probabilities of rare events. What I'm going to talk about, of course, is just part of a much bigger picture. For example, we recently did some work for the Swiss Nuclear, the NC, the Swiss Nuclear Federal Institution for Nuclear Safety, on the future risk for nuclear power stations in Switzerland. What that involved essentially was using something like 25 years of data recorded at the sites, maybe as much as 150 years of data recorded elsewhere, to try and estimate events with annual probabilities of 10 to the minus 4 or 10 to the minus 7 in some cases, out 40 years for all kinds of risks. I'm pleased they didn't put tsunamis on this list, but it was a close-run thing. They were worried about extreme air temperatures, of course, but also extreme river temperatures, because that influences how quickly you can get heat away from a nuclear power station. rainfall, snowfall, snow load on the roofs of buildings, and lightning strikes, for which we had about 10 years of data. But of course, all the modelling we did for that was just going to be then used as input for models used by the engineers at the individual power stations, trying to figure out what evasive action they might need to take to evade major events in the future. One thing we fortunately persuaded them was not going to be something they could deal with easily was the risk of major sandstorms coming up from the Sahara, which they do every 500 years or so. Trying to estimate the risk of that when there might be one in the historical record if you're lucky, we just said to them, well, just switch it off. Just make sure it's not working by the time the sand arrives to clog up the air vents. Another study we're about to undertake is of flooding on the rivers Eure and the Rhine up to about the year 2100. Of course, we're going to do extremal analysis of measured data, of regional climate model reanalysis data, and try and make forecasts based on that. But then that's going to be used as input to a complicated model, an event tree model of blockages of rivers, the behavior of sediment, and so on and so forth. So the thing I'm going to talk about, the tiny piece of ivory, of course, is part of a much larger piece of furniture. Okay. Why are we dealing with extremes? Well, essentially because the extrapolation from the fit, if we think of the distribution of events we might see, extrapolation from a fit to an entire data set can be misleading for a whole variety of different reasons. One is that different mechanisms may apply in the tails of the data. Really extreme heat waves, maybe not like ordinary hot days, just a bit hotter. A second reason from a statistical point of view is that different fits to the bulk of the data may give very different tail estimates. And in particular, the tails of the Gaussian density may give you very, very poor estimates for probabilities of rare events. One of the purposes of my standing here before you today is to try and assassinate the Gaussian distribution as in being any possibility of it being used for rare events. Don't. Second reason is, apart from the tails of the scale of the univariate Gaussian distribution, is that if you look at the tails of the bivariate or multivariate Gaussian distributions, these can severely underestimate the probabilities of rare events, essentially because they predict that at very extreme levels, events will occur independently. And here I've put a formula I couldn't resist. I'm sorry, I have a mathematical background. Here is the so-called formula that killed Wall Street, according to Wired magazine. The story goes that when pricing risks on Wall Street, the Gaussian copula was used to do so, and that led to the financial crisis because they badly mispriced the possibility of simultaneous bad things happening. Of course, it's a story, but the problem arises also in looking at climatic events. Okay. And what I want to do on the next two slides is first of all illustrate the first point I've just made about the probabilities for Gaussian tails. What I show here is on the black curve, just a Gaussian distribution, and as the red curve, a t distribution with 20 degrees of freedom, which we teach in our elementary statistics courses, is quite difficult to distinguish from the Gaussian distribution. It's not so easy, despite what you can see in the picture there. And what you see at the bottom of the slide is the ratio of probabilities for events beyond 2, beyond 3, beyond 4, beyond 5, going further and further out into the tails here. And you can see that around 2, the probabilities are about the same. But then when we look at probabilities when we get out to looking at events beyond here, if we were to use the normal model rather than the t, we underestimate probabilities by a factor of about 60. And then when we go further, out to 7, we're underestimating probabilities by factors of 130,000. And clearly that makes a big difference when you're pricing extreme risks. So that's the first point. Gaussian fitting distributions to the bulk of data and extrapolating can be badly misleading. Second point, Gaussian tails and conditional probabilities. What I'm showing in this picture here, up here, what you can't see, but the sides of the two distributions, the marginal distributions here, are the same in both cases. They're actually rather skewed distributions. And what you see in the plot on the left is the upper tail, exaggerated, of a bivariate Gaussian distribution. I've just transformed it. This is the graphical version of the formula that killed Wall Street, the thing I showed you before. Okay? And what you see here is the probability of being above, say, 6 on this axis, conditional on being above 6 on this axis. The ratio of the number of dots in this square here to the number of dots in this part here, this rectangle. And here what you see is how that probability changes as I increase the two lines up into the top, from your point of view, right of the picture. And what you see is that the probability goes down here. You can see the grey line goes down. It goes down, and eventually it hits 0. Okay? So the probability, if you have a really extreme event on the horizontal axis, it will have the probability of a correspondingly extreme event on the vertical axis is eventually 0. The events become decoupled. Okay? If on the right, you see something for a more appropriate modelling for extremes. And here you can see, or rather you can't because of the grey line behind, but the probabilities here converge to something that's constant as the event on the horizontal axis becomes rarer, it does not decouple from what goes on the vertical axis. And of course, that's what you would expect to see if you think of extreme temperatures here in Paris and then not very far away. You expect them to be highly correlated. Maybe not with extreme rain, because perhaps extreme rain takes place on a small spatial scale. But certainly for certain extremal processes, we expect to see what's happening on the right, not what's happening on the left. Okay, so the crucial element is space and time dependence at different scales and actually in different topologies. As I just said, heat waves are large scale. Depending on whether one's talking about heavy winter or summer rainfall, it might be on a large scale or a local scale, depending on whether it's a big system or a convective type of rainfall. If you're dealing with heavy snowfall, that doesn't depend just on your location on the map, but also on your altitude. It can be raining in a valley, and then 2 kilometers away it can be snowing heavily at the top of a mountain. So there you have to think of distance as being related not physical distance on a map, but also what the mountain climber has to do to go from one place to the next. And then high river flow, an example I'm going to talk about in a little bit later, depends also on the river network and its topology, as well as on geography. The problem is that classical statistical models are typically inadequate for modeling extremes because they involve inappropriate assumptions about dependence. And here's an example. For some reason, when we think of bad things happening in Lausanne, we tend to think of them happening in Zurich. I can't think why that should be. But anyway, this is a simulation of so this is Zurich here, Lake Zurich. This is a simulation from a classical statistical model of extreme annual maximum rainfall, simulated using a Bayesian hierarchical model. Some of you will know what that is, others won't. It's just it's a classical type of model. And the problem, as you can see from the map, is there's no spatial coherence, because the model assumes that somehow conditional on certain quantities, that the events at different parts of the map are basically independent. And that's clearly inappropriate. So what you're going to do if you try and forecast risk of flooding is you won't get the sort of spatial association that's needed. And that's the problem. Now, of course, you can fix that by using a Gaussian copula. That would be a simple fix, and it could be applied in this case. But we're still going to have that problem that risk might be underestimated because of the problem I mentioned, the formula that killed Wall Street. Okay. What I'm going to do now is to talk in a bit more detail about statistics of extremes. Firstly, talking about univariate extremes, and then I'm going to very quickly talk about how in the last fewer than 10 years, we've been able to go from fairly good modeling for univariate quantities to highly accurate modeling for multivariate quantities, and in particular dealing with spatial, temporal, and so on types of dependence. And this is increasingly, the methods I'll describe are being increasingly used in other applications in climate science and so on. So, to start off with, the Gaussian distribution arises when modeling averages, and it's mathematically underpinned by something called the central limit theorem. That theorem applies to lots and lots of quantities, and that's why the Gaussian distribution is ubiquitous when we think about averages. If we think about maxima, maxima are influenced by the bulk of data, but in a different way, because they're somehow forced to the extremes. More and more observations, the maximum gets bigger, right? But it's somehow always distinct from them, whereas the average is a combination of them all. And there's an analogous theorem, a theorem analogous to the central limit theorem, the so-called extremal types theorem, which tells us what sort of distributions we should use for modeling maxima. And it's this thing that's on the screen behind me, the generalized extreme value distribution, and which is now widely integrated into modeling for extremes. The basic idea is extremely simple, and it's called max stability. It's in words, we simply say that what that means is that the maximum of 100 consecutive years of data has got the same distribution as the maxima of the individual maxima for the 10 decades. And what that means, what that implies mathematically speaking, is that only certain distributions can emerge when we look at maxima. What it gives us, this idea of max stability, is a coherent basis for extrapolation to rarer events. It tells us what structure the tails of distributions ought to have, at least if in this pure mathematical world that this transparency is concerned with. The generalized extreme value distribution can also model different types of tail behavior, and it can be extended, modified to deal for other types of data, not just maxima, but also high threshold exceedances, which are much more commonly used now in modeling of extremes. So here are just 3 images showing you how the generalized extreme value distribution differs from the Gaussian. Behind you can see, on this one you can see the gray. This is the Gaussian distribution. Over there you can't quite see it. And over here you've got the Gaussian distribution again. And here is the generalized extreme value distribution in 3 cases. In this case, it looks very close to the Gaussian, and that's not quite a coincidence. Here is the Gumbel distribution, which would arise, for example, in modeling very typical model for rainfall. Here is the Frechet distribution, which has got much heavier tails. It's not really visible here, but out here, the tails of the gray and the black are really radically different. We get much higher probabilities when modeling using the generalized extreme value distribution. Let me now shift gear again slightly and talk a little bit about flooding in Europe and about how one might go about modeling this using these techniques. Spatial dependence, of course, is an essential determinant of flood severity, and it's important to get that right. What I'm going to talk to you about very briefly is a study that we did recently on trying to model high flows in the upper Danube basin in southern Germany. You can see what we had essentially was 31 gauging stations, 50 years of daily data from those. As you can imagine, but also as you can see, the topography is highly variable. Down at the bottom of the picture here we have the Alps, above is the German plain, and here's the Danube and various tributaries to it. And the red blobs show you where the gauging stations are. And what I'm going to describe is just a little work we did on summer floods due to rainfall, not due to snowmelt. That covers about 40% of the major floods. Okay. Just to show you how the generalized extreme value distribution works in this context, what we did was to fit a regionalized generalized extreme value distribution to data from all the stations, all 13 of them, with those parameters, the 3 parameters that I described, varying with location. So they depend on altitude, catchment, and so on and so forth. And as you can see in the plots here, there's a very good fit to large individual flows at the different stations. On the left, you can see the behavior at station 7 on the Danube. The diagonal line, the solid line there, if the points lay exactly along that would be a perfect fit. And if they lie in between the dashed lines, that's a good fit. And you can see this is fine. You get a similar behavior here at station 13 on the River Inn. Again, these are large flows here. These are smaller flows here. You can see the fit's pretty good marginally. The problem is, I keep on getting used to doing this. What we can get from that is models for the marginal output. We can give, in this picture here, I've mapped 100-year return levels for the flows along the river network, estimated from the marginal distributions. So you can see on the right, at the bottom, there are much higher flows, the order of 7,500 meters cubed per second, whereas the green parts at the top or on the left show you much smaller flows, of course. And what that is already a useful model for daily discharges at individual sites, which could be used, put it then into hydrological modelling and used for risk assessment. But of course, what that doesn't give you is the joint properties. It doesn't tell you what is the probability of simultaneous heavy flooding here at site 30 and downstream here at site 1. Okay. There's a problem because the dependence in this particular case depends upon the topology of the river network. What you see here between sites A and C is a fixed Euclidean distance, a fixed geographic distance as the bird flies, and the distance between A and C is the same as the distance between B and C. A bird going from one to the other is going to have to do the same work. But of course, the relation between A and C and the relationship between B and C as far as water is concerned, as far as the fish goes, is quite different. Because the water that goes through C is subsequently going to go through A. But there's no necessary connection between the water that goes through B and the water that goes through C. So therefore, what we need to do is to take into account the property that these B and A are related, and C and A are related, but B and C are not related when we think about combining those and looking at risk. Okay. What we can do is to summarize extremal coefficient in something that's like the Pearson correlation coefficient that you will have learned in your first course in probability and statistics, but it's something called the extremal coefficient. It relates, if you like, the probability of an extreme flow in this particular context at gauge S, at one side of the river, along the river network, conditional on there being a similarly extreme flow at gauge T elsewhere on the network. And on the scale here, rather than going from -1 to 1, we go from 1, where the relations are fully dependent, up to 2, to where they're completely independent. And what you see on this graph, on the left, is the estimates of theta, S, and T for Euclidean distance as the bird flies. So what we've plotted here for the flow unconnected pairs in red are which you see there, they're lower, so that means these are sites that are more dependent, or other pairs of sites that are more dependent. What you see I'm sorry, I should probably be using this thing, but it's so sensitive. Oh, there we are. Okay. So these ones here, these are flow dependent. The black ones above are flow unconnected. And you can see, of course, there's lower dependence between the ones that are not related by water flowing through them. But you can also see a lot of variation. There's not a very strong relationship between Euclidean distance and dependence of the extremes. Whereas on the right, we've plotted something which we call hydrological distance, where you can see much greater. Over here, you can now see this makes a rather nice, clear pattern of dependence. Okay, with, of course, the flow-connected things being closer to more dependent, and the flow-unconnected sites being less dependent. I'm not going to show you a whole bunch of equations about max stable models, but I'll be delighted to do so this evening at 7 o'clock, when I understand that some of you are having a meal. But Philippe and I will be thrilled to explain all the mathematical details of max stable processes for anybody who's interested. Max stable modelling for complex extremes, as I said at the beginning, has been a main focus of activity in the statistics of extremes over the last decade, and there have been a lot of methodological advances. Basically, what these describe are spatial and space-time analogues of the generalized extreme value distributions, which give dependent structures that are appropriate for rare events. So they get the dependence that I showed you on the right-hand side of that earlier slide correct. Okay? The same underlying mathematics applies as for the generalized extreme value distribution, and as the name implies, max stable processes, they're based on the same basic idea. They give us what one might think of as being the right sort of extrapolation to rare events. There's quite a wide variety of models that have been developed by colleagues all around the globe, many of them based on Gaussian processes. And for those of you who've done modeling with Gaussian processes, that will mean you'll know that that means they can be quite flexible things for describing lots of different sorts of dependence. We can fit them using standard techniques, and we can assess the quality of fit, again, using standard ideas. And then we can use simulation from the stochastic simulation from these fitted models to estimate risk, and then use that as input to bigger processes. Just to show you how the max stable fit works for the river data I showed you, what you see on the left now is the plot of the thetas, the extremal coefficients against hydrological distance, and on the right you see this equivalent thing for a model, a max stable model, and you can see, okay, it's not perfect, but it does a pretty good job of capturing the dependence. And you get similar behaviors for triples of gauges, quadruples of gauges, and so on. So we get the dependence broadly correct. Okay. Here again, I'm sorry, it's Zurich getting wet again. What you see here are simulations, because it's rather difficult to visualize simulations on a river network, and I'm showing you here are simulations from max stable models fitted to summer maximum rainfall in the Zurich region. And what you see here are three different spatial dependence models. On the left, one that doesn't look very realistic because there's too much structure here in the extremes. And what you see on the center one and the right-hand one is much more realistic spatial dependence for extreme rainfall, which then extrapolates nicely in lots of different directions. So max stable models allow sound extrapolation to rare events in space and time, and we've now applied them to, we and others have now applied them to many climatic phenomena: heat waves, winter temperature minima, extreme snowfall, extreme rainfall in space and time, high winds. We're currently working on European windstorms, and so on and so forth. One can incorporate the effects of large-scale weather patterns or synoptic events if one wishes to do so. Of course, it's going to be essential for doing proper system-based prediction, for example, such as the NAO and the NC and such like. One can put in time trends. One can, at least in principle, do correlations with reanalysis data and so on. Of course, unfortunately, there's plenty yet to be done. Or I'd be looking for another job, I suppose. We need to know in a principled way how to do downscaling, to do proper downscaling for extremes from large-scale predictions to detailed local things, fits to very large data sets. The use of anecdotal data, that in 1500 the flooding in such and such a church reached this high, but we have no other data, and so on and so forth. But we already have a body of techniques that can be used. I've put here a couple of references in case anyone is interested. I'm afraid they're to our own work, but there are some other, just because this is the most recent review that I know of, which mentions all the other ones. This is the top one here. There's also a paper which this seems to be quite widely cited, the second. And for those of you who are actually doing modeling, there is an R package, Spatial Extremes, written by Mathieu Ribaté. Thank you very much for your attention.
So it's a pleasure to be here. I'm very lucky. For many different reasons I'm going to explain. But first I would like to acknowledge my colleagues. Alexis Hanard, who works at CNRS in Buenos Aires. Aurélien Rib from Météo France in Toulouse. And Francis Wyers, a colleague from in Canada. This mainly has been part of the project called DADA, which is called Detection Attribution and Data Assimilation. So I'm going to explain what is detection attribution. And why I'm lucky, because this morning Sonia and Valerie did a great job to explain how the climate works. And also Anthony speaks a lot about statistics, and as you can see, detection attribution is between the two. And I think economists could be of great help because also they are great statisticians. And so they could help also maybe to to solve some of my problems. What is detection? As you know, it has been said before, but it's to try to show that you are above a certain significant level. So in insurance contract, there's always a footnote. And so you can look at the footnote here. And the footnote says what it is. It's statistical change. It means it has to be beyond what can be explained by the internal variability alone. Okay, so there's a statistics and there's a notion of internal variability of the system. So that means you need to know what is the variability of the system and you need to be above that. So it's fairly hard, in fact. But this picture was shown this morning, and this sentence is from the IPCC report, but this picture shows basically, you don't need, in fact, fancy statistics to see warming. Okay? And so I'm not going to spend too much time on that. I'm going to spend time on attribution. Okay? And again, we have to look at the footnote number 2. And the footnote number 2 says causal factors usually refer to external influence, so external forcing, okay? And they have to be of different nature. But what's very important is the word causal, okay? There's a cause, okay? So you don't simply have to explain, to say there's a change, you have to explain the change. And that's not very easy to do. In fact, you need more just to say it's a correlation between, for example, increase in CO2 and global warming. You have to show that it's consistent with the expected response to the system, but also inconsistent with other explanation. So it's fairly hard. Speaking about external forcing, we mentioned many this morning. Like here, it's just an illustration of Tambora in 1815. So everyone knows what is Tambora now because it's a volcanic eruption who change the climate. Basically, there's a cooling effect. So volcanic eruption is a kind of an example of external forcing. Of course, since the Industrial Revolution, we move away from sailboat, and now we have the increase in CO2. And so that's the anthropogenic forcing, which is viewed as external too in some sense. So now if I want to say, what do we need to do detection attribution? Well, we need different parts. We need the observations, and it's not very easy to get, because today it's fairly simple to get very good data, but if you move back 50 years, but 100 years, or maybe 1,000 years, then it's become very complex. So you have a problem with that. You have a lot of error in this. Then also you need to know what is the external forcing. And then there's the fourth part, which you need to understand the system, which means you need a model. And here, what I mean is not a statistical model, it's a physical model. And last but not least, you need also to have an estimate of the internal climate variability of the system itself, which is not very easy to do for many different reasons. So I'm going to skip this. So in terms of attribution, we have different results. So that's from the IPCC report. But basically, you can see, just to note that before we have, in terms of causality, we have likely, observed warming is likely to be due to increase in greenhouse gases concentration. And now it's becoming, in 2007, very likely. And now in 2013, extremely likely. So the question, how they get these kind of statements? And as I said, we need statistics. And the simple model in statistics that everyone knows is linear regression techniques. So that's what people do. But there is a big issue. Suppose like you want to demonstrate that smoking can cause lung cancer. What you have, it's a lot of people who are smoking and a lot of people who are not smoking. So that's fairly easy. But here, we have only one Earth, to my knowledge. And so not only we have one observation, but it's a very long one in terms of dimension. You have space and time, so it's a huge vector. Okay, so that's an issue. But the key idea, and it was already said by Sonia and Valerie, is to use climate models. They produce, in fact, other Earths, like we have more. And if you look at this graph, this is the black line, it's the observations, and then this is a run of a climate models with different ensembles. And here you have all the forcing you can think about. And then if you have only the solar and volcanic forcing, which are external forcing, you get the blue curve. So the question is to say, when is it different than the black curve? Okay? And also, what is the contribution of the anthropogenic forcing? So that's basically how the game is played. So to have a quick summary, you have here the system, the climate system. You have anthropogenic forcing, let's say natural forcing. You have the internal variability, and you have the model error. Which I mean by that, there's a lot of errors here. But if you look at the climate model, let's say, of the IPSL model in France, it's going to have some error of representation of the system could be different from the NCOR model. So you have to take into account this error between models. There's no perfect models. So what people do is they run the model with the historical run. That means they take everything, and then they just use this one, let's say, and then they compare. So that's basically how it's done. And then when you have that, you take the observations, and then you take the anthropogenic forcing response and natural response, and you just do a linear regression, and you are done. So you could say this is very simple. Well, it's not that simple, because we have to estimate the variability of the system, okay? The error, the sigma, the matrix sigma, which is a huge one, and you have very few runs, okay? But if it was sparse, that means if you move away from a short distance and say, oh, the dependence is 0, that would be fairly easy. But because of what's called teleconnections, this big matrix is not sparse. So that's already a problem. Also, as I said before, the climate model itself is not perfect. So if you take a different climate model, you have a different answer. So you have to take that into account. And also, there is an error in the forcing and the observations. And also, if you want to deal with extremes, you have to move far away from the Gaussian distribution. So a possible solution, some people have been working on that, but you can deal with regulation of covariance matrices. You can use error in variables models. Here it's a list in some sense, but so far I don't think there's a complete statistical model to deal with all of that. So we are still, it's a work in progress for that. So that was number one. Number one was linear regression techniques people are using. There's another approach, which is called the FAR approach, the fraction of attributable risk. And what is that? So here, suppose like you have the 2003 heat wave, and the question you ask is not, oh, what is the trend? You're not looking for, you don't want to do linear regression anymore. What you want to try to answer is to say, what is the probability of having kind of a heat wave in 2003 if there were no anthropogenic forcing, or if there is one? Okay, so it's like you take a smoker and a non-smoker and you compare. Okay, this probability. And to do that, people like Peter Stott and Mike Shannon and colleagues, what they say, oh, we are going to kind of impose some SST conditions, sea surface temperature condition, to a very fast numerical model. Basically, they run the model 10,000 times or more, and then they compute empirically this probability, P0 and P1. So basically, this is just a relative ratio of two probabilities. So the probability in the world that may have been, so without CO2 forcing, basically, and the P1, the probability of being greater than the heat wave in the world of today. Okay, so you do the ratio of two probabilities. There is an issue if you know a little bit of statistics or even a little bit of math, you know there is an issue because if you look at a small probability P0 and a small probability P1, and you do P0 divided by P1, it's 0 divided by 0, you can guess it's going to be very unstable. So to compute that is not trivial. That's why they need a lot of experiment, 10,000 experiments. We are very costly. And I can come back also to this. Why do they use this ratio here? Why do they use this statistic, the 4? Okay. And in fact, it's clearly, no, it's not that clearly, but it's related to the problem of causality. So I suppose that economists are well aware of this problem, is to try to demonstrate, as I say, detection is to see there's a change, and attribution is to say what is the cause of the change. And basically, the most classical way to do that is to think that to show that A implies B is just to say that if A didn't happen, then B will not be happening too. Okay, so it's called the counterfactual definition, and it's go back to a long time ago. So we work a little bit with Julia Pearl, who did a lot of work on causality and tried to use this kind of framework, theoretical framework, to explain what is causality in respect to climate studies. So this, I'm going to skip that. But basically, Anthony mentioned a hierarchical graph. And this, if you want to speak about causality, for example, you can sometimes use oriented graph. Let's say you have a low pressure system, and then it could influence the barometer, and then it could influence the rain, and the rain could make the road wet. But you can see the barometer is not dependent on the rain. So with this kind of framework, oriented graph, you will like to explore the question of detection of attribution. And one issue, usually, if you just use the data itself, the observation, you will have a problem to prove causality. You can just show correlation or dependence. So what you need to do, you need to experiment. And the way to do the experiment is very simple. For example, I could give a barometer to my son, who's fairly young, and he could move the needle by itself. So you do an experiment, and you see, oh, this doesn't change the weather. So it's the weather which is changing the barometer, it's not the barometer which is changing the weather. So doing an experiment is the only way to show causality. Okay? Also, my son will break it, but that's a different story. But there is a difference between causality in terms of necessary and sufficient causation. So what we like to make as a distinction is to say, is it a necessary cause or a sufficient one? Okay, an example of that is clouds are a necessary cause of rain, but not a sufficient one. Okay, so you can look at that, and then it's possible to use a mathematical framework of causality like this, but what's fairly interesting is the probability of necessity, Pn, and the probability of sufficiency could be used in climate studies. And because the forcing, if you remember, the climate forcing is external to the system. You know, volcanic eruption, solar irradiances are external. So in this case, it's possible to show that the work by Stott and colleagues, the far, in fact, correspond to the Pn. So with doing this experiment with climate models, in fact, they show necessity. They could show also sufficiency by computing PS. But I think it was interesting to make the link between causality and the FOR, which is very much used in climate studies. So for example, if I'm coming back to this graph I showed before, if you run the models, with all the forcing, external forcing, or only with one part, let's say the natural forcing. And if you fit, for example, general extreme value distribution, which was shown by Anthony, you can compute this probability P0 and P1. This is just a toy example, and you can conclude sentences like that. CO2 emission are very likely to be a necessary cause, but it's not necessarily a sufficient one. Okay? So I think it's interesting to show that it's not, there is a difference between the two, and it gives maybe more way to understand the question of consequences. So this I'm going to skip. So still, I didn't speak too much about the inference here, and I'm going to spend a few minutes on that. So now we have to come back to the definition of an event. I've been fairly vague about what is an event, okay? And every one of you, in fact, could define an event of interest. For example, in detection attribution, people look at the event of X, variable X, let's say, is greater than a given temperature, like the heat wave. Okay? But you could say, I'm going to look at a different event, who could be X is smaller than something else. Okay? So how to define the event is very, very important, I think. And also, it could simplify the computation in terms of statistics. Because as I say, one difficulty is to have 0 divided by 0. I mean, when I say it's not exactly 0 divided by 0, it's small divided by small. So here, if I come back to this graph, the far view, it's 1 minus the ratio of the two probability. And the question is to say what's happened, if you're interested in extremes, is to say what's happened when U is large. Okay, that's what people want. If you want to deal with extremes, you have to say U is very large. And so you have the numerical model side here. And then you have the observation side. You have the FAR, which is the probability of necessity in some sense. And you want to estimate these two, P0 and P1. In fact, you want to estimate the FAR. What's interesting, in fact, if you look at the FAR, and you bridge that with extreme value theory, when the threshold is going to increase, some people could think like, oh, it's 1 minus P0 divided by P1, and when U is very large, it's going to be either 0 or 1. But no. If you look at a Frechet distribution or Gumbel or Weibull distribution, here I take a Frechet distribution, and P0 is a Frechet, let's say with scale parameter equals to 1, and I multiply the scale parameter by 2. And if you take the ratio of the two and go to infinity, it's a constant which is neither 0 or neither 1. And so to determine what is this, it's kind of funny because it's very stable in theory. You can do the same kind of example with the Gumbel or the Weibull distribution. What people do in practice, as I say, they don't, in fact, use a statistical model, they just use brute force. They run 10,000 or 20,000 experiments, and they do the estimate like that. So basically, if you do this kind of thing, if the blue curve is the correct one, if you do the empirical ratio, then you get something which is going to jigsaw kind of things, and the estimation is not going to be very good, especially here. I take a return level of 30, but if I take a return level of 200, it's going to be very wide. So we have to deal with that. And right now, we are developing a different kind of FAR. So we call it a small FAR, which is not that far from the FAR. And it's instead, what we are trying to do is not to fix U, which is a return level, but much more the return period R. Okay? And we are asking a question, for example, if you have a time series, what is the probability that the max over, let's say, if R equals 100, you take 100 years, And what is the probability that the last year is greater than any other years? If the system is stationary, it's very simple, it's 1 divided by R. But then you want to compare this event with, in a different setup, which is the setup with anthropogenic forcing. So you have this ratio of 2 probability, and if you use that, you can prove, in fact, this FAR of R is very close to the FAR of U, the other one I showed before, and they go to the same limit for the 3 cases, gumball, fresh air, Weibull. And here it's a dotted line, it's the new FAR, and the plain line here, it's the previous FAR. So in some sense, by just changing the definition, you get the same limit. What do you gain doing that? Well, in terms of inference, now you can see it's an empirical inference, but still what you get is much better estimation. Here you have something which is move a lot. Here it doesn't move that much. It's much more continuous. And the confidence interval can be proven that it's much smaller. So by just changing the statistical inference technique, you can improve the estimation of the quantity of interest. I'm not going to speak about that, but we did that also for max stable process. But I'm not going to speak about that. So I'm almost done, and I'm going to make a few points. So my goal today was to speak about, of course, detection attribution, but basically detection attribution, I think it's based on 3 different things. One, it's climate models, climate observations, but also statistics. And within statistics, there is this field of causality which could help. I would like to stress again, like in terms of uncertainty, maybe you know how to do it, but the question to estimate natural variability, model errors, and it's fairly hard. And why it's fairly hard? Maybe that's a difference between economics and climate. It's here. We have the temporal dimension, that's for sure, but also we have the spatial dimension, okay? And which is huge in some sense, the spatial dimension. If you look at the output of a climate model, it's huge, and so people usually just project that with PCA or EOF, which is the same. What we would like to work on with my colleague is to try to reduce the fact that people use events, but they are thinking about realization, which is different. That's, I think, also a good way to bridge, I think, statistics and observations and numerical model. It would be to define very clear design of experiments setup to really answer the question of causality. Here I'm going to finish by mentioning, in fact, if you want to learn more about statistics of extreme and extreme value theory, there is a workshop, a summer school organized by Pascal Yu in Cargèse, nice place. And also you can go to Lyon in 2016, in June there will be a conference, a summer school on that. I listed a few papers I wrote with colleagues, but I would also like to insist on there is a journal which is called Weather and Climate Extremes, and we have a special issue on detection attribution coming soon, and I think this could be of interest to you. I'm going to finish by a picture from the far side. Thank you.
Okay, so good afternoon, everyone. So I'm an economist, and I'm going to talk about my talk will be a reflection about how we can model catastrophes in economics, and in particular in economic model of decision making. And the way I will link my presentation to the previous ones is that they talk about the way to model risk and extreme events. But at the end of the day, if we want to think about decisions, we need to find a way to measure the consequences of this risk, the realization of this risk. And so we need to measure the intensity of that as an objective. And so my presentation will try to talk about that. So it's, at the end of my presentation, I will present briefly a paper I have written with Carole Bernard, who is a statistician at Waterloo, and Christophe Renberger, who is a postdoc in Toulouse. So as in the talks this morning, I'm going to start with a figure with an increasing trend. But this one is not really about the production of CO2 emissions, it's about the production of economists. So it's, with my colleague, we have counted the number of times the words catastrophes and disasters appeared in publication in economic journals. So it's top generalist journals plus the top environmental economic journal. And you see that there is an important trend which suggests that there is, of course, an increasing interest of economists in these topics. I'm not sure I should interpret this. Maybe there is a part of labeling. But for sure, there are, if I take a sample of publications, there are a few topics that really attracted a lot of attention. One is the link between catastrophes, disaster, and asset prices following the financial crisis, and also the growth in our economies. And another one is climate change. However, I think it's fair to say that dealing with catastrophic risk in economics models is quite of a challenge. I'm going to try to give you two examples to illustrate this challenge. There is a fascinating book by Richard Posner published 10 years ago about catastrophes. And in this book, he suggests that maybe we don't pay enough attention to several big catastrophes that we face. This includes climate change, but this also includes bioterrorism, asteroids impact, and a few others. And in this book, he suggests that we may try to use economic analysis and benefit-cost analysis to estimate the benefit of reducing this catastrophic risk. But of course, if we take the most extreme risk, like human extinction, for instance, then we get into difficulties because we need to compute the probability of this risk, which is already a big challenge, as we have seen before, but also a sort of what will be the benefit of avoiding this risk. So in other words, what will be the cost of that. So what he tries to do as a very first attempt, he takes an estimate of a future Earth population, which he multiplies by the value of statistical life, and he gets to a very high figure of several hundreds of quadrillion. And I think it's a bit strange as an exercise. I think it's very natural for an economist to do that exercise, but it's a bit strange. Here we are talking about a massive risk. We are talking about risk in the future. We are using value of statistical life, which usually is estimated through a wage risk trade-off or transportation risk, and we apply that to big catastrophes. So there is something that with which I feel a bit uncomfortable with that exercise. Another example to illustrate that it's a bit challenging to deal with catastrophic risk is related with a paper by Martin Weitzman, which has been cited with a lot of frequency in the economics literature. And this paper essentially suggests that if we combine some specific modeling assumption of a risk, which he calls fat tails, it relates to what has been presented before me today, and together with some specific assumption about the utility function, then we get into a situation in which there is a sort of infinite benefit of preventing climate change. And so we cannot simply do cost-benefit analysis because we have indeterminacy here. Of course, this paper has been criticized in the literature, and there are still ongoing discussions. In economics and in economics models, when we start thinking about risk, a key notion is the notion of a risk attitude. What is the risk attitude of a decision maker? And the instrumental concept here in our field, at least historically, is the concept of risk aversion, which has been, there is an index of risk aversion, which relates to the curvature of a utility, and this is the index was proposed by Pratt 50 years ago. And essentially, it captures the attitude toward the risk on wealth. The title of my talk is Catastrophe Aversion. So I will attempt a definition below, but essentially I think of catastrophe aversion as a collective attitude toward a risk on wealth and also a risk on life. We have seen this morning by Antoine all the impacts in terms of physical impacts of climate change. So I think it's important also to account for physical risk here. Okay? What do economists do when they examine catastrophes? Most economic models, they consider a representative agent and they consider a risk on aggregate wealth. The presentation you will see tomorrow morning, most of them will do this. And it's very natural. This is the most natural way to model this. But typically, when we do this, because we consider a representative agent and we consider a risk on wealth, the very concept of catastrophe aversion is equivalent to the concept of risk aversion in this model. And so in the rest of my talk, I will propose an alternative approach. It's really complementary to the standard approach, I will say, in economics, but I think it's more, it uses some inputs from other fields like statistics or social choice. And I will try to share with you how we can alternatively model catastrophes in economics. And I will also present some recent references. So let me start with a very simple example. And it will help me to introduce the definition of what is a more catastrophic risk. So here I consider a society with only two people, two individuals, I, and two equiprobable states, S. Okay? So let's say that 1 means bad state or dead, and 0 means alive. Okay? So we see two situations here, A and B. Okay? In situation A, agent 1 is dead in state 1, and agent 2 is dead in state 2. Okay? So we have a negative correlation here. And in situation B, both individuals are dead in state 1. Okay? Let's now, from this very simple situation, compute the distribution of fatalities in the society. Situation A, we know that there is one and exactly one person dead in each state. So we know that there will be exactly one death in that situation. Okay? So the distribution of fatalities is degenerate. It's simply probability 1 to get 1. In situation B, it's different. Either everybody dies or nobody dies. Okay? And so you can say that the distribution B, situation B, is more catastrophic in this sense because you have a possibility that everybody will die. And so that's an example of a definition I will use for a more catastrophic situation. It's called the mean preserving spread of a distribution of fatalities. In statistics, I think it's called the convex order. And basically, we keep the distribution, the expected number of fatalities the same, because we cannot make everything moving together, and we just change the spread. Okay? Okay, so that's my starting point to define what is more catastrophic. Okay, so first question, and that will take me a little bit of time to think about this. Should we be intuitively catastrophe averse or catastrophe prone? I guess many people in the room, as insurers, you are probably catastrophe averse. We don't want correlated risk. Okay? Here is another example for the government, and very often I will take the perspective of government in my talk. US president and vice president do not travel together on Air Force One. They don't want the risk to be correlated. However, there are other instances, other contexts in which we may want to be catastrophe prone, according to my definition. Here is one. This one is provided in the seminal paper by Schelling about the value of life. And he takes this example. He says, suppose a family of 4 persons must fly, so same context, and this family has the choice between taking one or several planes. Then he suggests that maybe they should take the same plane because in this case they would avoid the prospect of bereavement. So in a context in which there is altruism and feelings, maybe we would prefer a more catastrophic situation, according to my definition. So that's just an intuition. What do we do in practice? I'm an expert in benefit-cost analysis, so I'm going to tell you the very first implication of benefit-cost analysis. So suppose, for instance, we want to choose between these two situations, and we use benefit-cost analysis. What will be the outcome of benefit-cost analysis? The outcome is that it will be indifferent. Why is that? Simply because in standard cost-benefit analysis, we multiply the expected number of fatalities by the value of statistical life. And as in these two examples, the expected number of fatalities is the same, there is no difference across these two situations. So you see, even these two simple situations, which seem extremely simple but also extremely different, with a standard tool to evaluate policies in economics, we won't discriminate among them. What about other regulatory agencies? There has been some, I don't have time to elaborate on that, but there have been different metrics used by regulatory agencies to try to account for that. So this complements standard cost-benefit analysis. However, as far as I understand, there is no foundation for these metrics. It's a bit postulated. There is no axiomatic foundation. There is no preference foundation. So it's the way I understand it, it's a bit ad hoc, I think. How do we behave in the face of this choice between situation A and B? Okay, so suppose we ask questions to people. It's a survey question, and we ask them to be in the foot of a policymaker. What will they choose? We try to collect with my colleague Christophe what has been said in the literature about this. So we found a set of papers. You can see them here. And so these papers ask questions to people about how they will choose between situations like A or B or variant version. And you see that we have mixed results. It's not obvious for people that we should be catastrophe averse. There is also catastrophe acceptance. Okay? We may be a bit confused by that. One possible explanation is framing. Some of you may know the work by Tversky and Kahneman. Kahneman is a psychologist who got the Nobel Prize in economics. And he proposed this very famous Asian disease example in which the policymaker has to choose between two distributions of fatalities, one that yields 400 people dying for sure, and another one, distribution B, that yields either 0% dying or 600 people dying with probability 2/3. So it's a similar trade-off. We can rank these two distributions according to catastrophe aversion, and B is more catastrophic. What did they find? They find that depending on the way the question was framed, the answers were different. Whether you frame it as a loss, people will be dying, or whether you frame it as a gain, you can save people, then the subject will respond differently. So this is a bit problematic, because if we really want to think straight about what we should do as policymakers in terms of prevention and accounting for catastrophes, at the end of the day, I guess we should have a feeling of how people react to this risk. And this study suggests that we should be very, very careful. If we use survey method, then because I guess these are hypothetical questions subject to psychological biases, then the way we frame the question may alter the responses. What about theory? There is a field in economics which is called social choice, and they try to think about what we should do as very often as a social planner or as policymakers, and they build on axiomatics. So they come up with very basic principles, and they try to explore the implications of these principles. The most standard utility function social welfare function that we use is a utilitarian one. So in most famous cost-benefit models of climate policy, which are called DICE, RICE, fund, page, they all use a utilitarian social welfare function. All of them are neutral to catastrophe, in the sense that they will not discriminate between the two situations I presented at the beginning. Why is that? The intuition is very simple. If you want to account for the correlation of risk, you need to have a social welfare function which is not separable, and all the standard social welfare functions are separable. So we don't account for the correlation of risk. There have been a few papers in the literature in economics that try to go further and introduce a preference toward catastrophes. And so there is a paper by Baumy and Zuber that allow for flexibility. Preferences can be catastrophe-prone or adverse. And there has been another paper in Journal of Political Economy that has been cited with some frequency by Marc Fleurbet. And this type of preferences is always catastrophe-prone, not catastrophe-averse. Why is that? Let me give you an intuition for why Fleurbet proposed preferences that are catastrophe-prone. I'm going back to the initial example. Compare A and B. The key point of these axiomatics, as far as I understand it, is that a catastrophic risk is more equitable ex post. Look at situation B here. You see that in every state of the nature, there are no differences. Either everybody dies or everybody is alive. So no inequality ex post. And so that's why we may want, contrary to intuition maybe, to have a framework in which we have catastrophe proneness. Okay? The most cited paper, I think, in this literature has been published in an operation research journal and by Keeney, and he showed in this paper that there is a link, even an equivalence, between more catastrophic and more equitable ex ante. Just again, using my tables, a very simple example to illustrate the Keeney result. Let's start from situation A. In situation A, four states of nature, okay, two individuals. It's extreme inequality because one individual is sure to die and the other individual is sure to be alive. Okay? Distribution of fatalities is degenerate, exactly one death. Now, let's introduce a risk transfer policy. Okay, as a conceptual framework. We transfer some risk from one individual to the other, from the more exposed to the less exposed. So we end up in situation B, in which people face the same ex ante exposure to the risk. They each have a probability 1/2 to die. Okay? If we do that, and if we assume risk independence, which is the case in my tables, there is a risk independency, okay? Then you have, it's a theorem, you have to, when you do a risk transfer, you have to make the situation more catastrophic. So this explains why this result has been cited a lot in the literature, because it tells us that there is a tension between a more equitable policy and a more catastrophic policy. They go against each other. If you want to introduce more ex ante risk equity, you introduce a more catastrophic aspect. Okay? To do that, however, he assumes risk independence, which is not really realistic when we talk about catastrophes, and that's the contribution we try to do with my colleagues. We try to extend the result by Keeney to a situation in which we allow for dependent risk. Okay? We essentially address two questions, two very simple questions. I guess my fellow statistician will find it's probably too easy, especially the first one. First one is, does more risk dependence always induce a more catastrophic situation? Then we show that it's always the case. It's an equivalence if you have only two persons. But to generalize the results, it's much more complicated, in part because it's difficult to define the notion of dependency with more than two random variables in general. So we try to do comparative statistics with that, and if you want to see the details, you can check the paper. It's on the website of the conference. The other question, question 2, is the question of Keeney. Does more risk equity ex ante always induce a more catastrophic situation? But we explore that, allowing for risk dependence. And here is, sorry for all of these numbers, it's not easy to read, but the idea is very simple. We start from a situation, so I'm going to show that this is a counterexample to Keeney's result. We start with situation A, in which there is no correlation between the risk, and we do a risk transfer. Okay, so we transfer a risk from the more exposed to the less exposed. Okay, you can, so in the initial situation, individual 1 is exposed to a risk with probability 1/2, and individual 2 to probability 1/4. And you can see below the distribution of fatalities for the situation A. Now let's do a risk transfer. So we do the risk transfer, but by doing this, we reshuffle a little bit what happens in every state of the world. And by reshuffling, of course, we change the correlation. Okay? What do we obtain? We obtain different probability distribution, and we can show, it's a counterexample, that the way we are reshuffling, we change the dependency, and we can obtain exactly the same distribution of fatality, or a more catastrophic one, or a less catastrophic one. Okay? So it shows that there is no systematic result. Our main contribution is to show that to exhibit a sufficient condition. The sufficient condition is the following: if we are sure that when we do the risk transfer, we are not increasing the correlation, then we know that there will be indeed a more catastrophic situation always. No, sorry, we are not decreasing the correlation. Sorry, I was not clear. So what do I take from this analysis? I think there is a simple message that there is a tension introduced by Kini between different objectives. You want more risk, ex-ante risk equity. You want people that are exposed to risk to be more equal. Okay. There is a tension between this desire as a policymaker and another desire, which is to have a situation which is less catastrophic. Okay. Okay, so I'm finished now. So I'm just concluding with my presentation. My main motivation was the following question: what should be our attitude toward catastrophic risk? I think it's a very complex question. It's a very challenging question, and it's for us economists, it's a key question, because at some point we will have decision-making models, and we need to capture the intensity of risk preferences toward these extreme events. So we need at some point to confront this question. Okay. So in our paper now, we just answer a very simple question, which is just a part of this big question. So we derive conditions under which more risk dependence and/or more risk equity always induce a more catastrophic situation. However, we ignore key component of what should be integrated into a cost-benefit analysis or an economic model. These are about the policy cost. These are about the expected life saved. We kept them constant, or the average is constant in different scenarios, and we didn't discuss at all risk-sharing opportunities, which of course in some cases is a big concern. So I guess the grand research program is to try to think about optimal prevention under catastrophe-sensitive preferences. So far in economics, we have been using specific frameworks like cost-benefit analysis or a social welfare function which is utilitarian or separable, which I think does not capture the type of catastrophe sensitiveness I introduced in my presentation. Thank you.
Thank you very much. So I would like to take just a couple of questions before we go for our break. Do we have any questions from any of the panelists? I see one hand up there. If you could also state your name and your organization when you're asking your question as well, please.
Hi, my name is Robert Muirwood from Risk Management Solutions. So this is for Professor Turek for the last very interesting presentation. I wondered if you could introduce, in the real world, we have a media which intervenes between action and policy, and the media obviously responds very differently to 50 people dying independently in road traffic accidents over the space of 12 months and 50 people being killed in a single incident. And actually politicians respond to how the media presents catastrophe and becomes a filter. And the filter instantly means that actually the response to catastrophes gets altered before it gets to politicians who are going to make decisions about it.
Thank you for this question. Indeed, that was one of the motivations for this project. We observe that in different circles, people are sensitive to the degree of catastropheness. And in particular, the media are very sensitive to events in which many people die simultaneously, which is a catastrophe. And this is not really captured in cost-benefit analysis. If you have, for instance, to choose between car transport or plane or train transport, you may want to compare the cost of this, for instance, the cost of the infrastructure. You may want to compare the expected number of lives saved. For instance, the train or plane, we know it's safer. But there is another aspect, which is the possibility of a big accident. And if we use standard cost-benefit analysis, we will not account for that. So I'm not sure. I'm not sure what we should do. But at least I think it's interesting to use our economic framework to see whether we should add an additional component here, which we can capture the possibility of a big accident. So I think it's a very relevant question.
One more down towards the front here.
I know I'm standing before you in the break. Erwan Michel Cajot from the Wharton School. One way to treat that is to forget about linearity in the cost-benefit analysis. To me, that's pretty straightforward. If you continue to treat everybody in the same way and think about expected loss, that's where we don't get it. If you move from linearity in your function to whatever function you want to use that's not linear, you don't have that issue anymore. It's not about just the media, Robert, it's the fact that you have, if you're an insurance company or the local emergency authority, you have a demand surge that's very different. Your capacity that you have to set aside to be able to answer a disaster, call it capital in the insurance sector, call it emergency teams in the emergency space, is very different. Dealing with car accidents, we know how to do that. Maybe there will be 3, 4, 5 cars that are hit. Commercial airplane crashing, immediately change a paradigm. You need 200 people on the ground. You need a very, very different operation capability that you don't have. So, we can talk offline, but to me, just the treatment of the function you're using in the cost-benefit analysis could be one way to handle that. But you know that already, Nicolas.
So yes, I tend to agree that we want to move from linearity. In fact, as far as I understand it, we really want to move from separability. But the next question is how we are going to move from it, and that was the purpose of my talk. It's not clear to me how we are going to integrate that. Some regulatory agencies, I presented a few, they try to introduce some metrics, but it's not really founded. So this is my search here. What would be the foundation?
Okay, well, not
I think that the preference for big catastrophes, in case of you can be in equality with other people, with other agents, is very common, especially in the regulation of insurance. In regulation of insurance, mainly, the preference is that everybody can be dead if there is an event which was not anticipated, for instance, big volcano catastrophes that we have seen in the 19th century. Because we think, the regulator thinks that the market will not fail. And to some extent, he prefers catastrophes for everybody being equal, than to escape from big catastrophes that can be very costly in terms of regulation. So I think it's a very common situation.
And final comment from down here.
Yeah, I'm Bob Pendyke from MIT. So Professor Davidson, so you suggested using generalized extreme value distributions. And indeed, they've been very useful for things like looking at hurricanes and storms, where you have lots of data. And the problem is that with things like climate change, where there is no data, there's virtually no data. You can hypothesize a fresh aid distribution, for example, but I don't see how you can estimate it. And the basic problem is think about whatever the distribution is, and you create the cumulant generating function, and think about higher cumulants, because that's what matters. You can't find the higher cumulants unless you have massive amounts of data, so I don't know what it buys.
Well, I mean, of course, one's got to do it indirectly. What one needs to do is to do a correlation between what we see now, for which we do have some data, and climate processes, and then try and use climate models to impute the future, and then hope that the correlation is stable. I mean, that's why my point about being modest and humble. We have to be very careful about how we do this. I mean, as far as cumulants are concerned, forget it. The fresh air distribution has has only a small number of them. So there's no way you can use them even.
Yeah, I mean, I guess you're right. If we're humble and we don't claim that we can say very much, it's fine. But it's a little bit like with the models, we can look at the tail of the elephant, but we can't say very much about the rest of the elephant.
Yeah, but the point is that the tail is what's interesting as an extreme value modeler.
I think we're looking at different tails here, but that's okay.
Cats and elephants. Yeah. Okay, thank you very much, and we'll take a short break until just after 4 o'clock. Thank you.